Okay, let me talk through this page in notes. The knot group detects the unknot. First of all, the unknot is exactly what it sounds like. It's unknotted, a piece of string with no knot tied in it. So it's just a very simple loop. There's a picture of it there in the dark green. Call it U for now. And here's the fundamental group of the complement of the unknot. Let me zoom in there a bit. That x0 is just an arbitrary chosen point. So there's really only one generator for the fundamental group. It's the loop that starts at x0 and goes over that single arc, the unknot, and back to x0. So the fundamental group of the knot complement, the knot group, is just the single generator and no relations because there are no crossings. Now that is familiar. If you have a single generator, no relations, then what you have is the integers. The isomorphism there is just see how many copies of the generator you are. That's the integer. If it happens to be the inverse of that generator, that's a negative integer. If it's the empty word, that's 0. So the interesting thing is that the knot group detects the unknot, which means that, as we'll see towards the bottom, there's a theorem that says that's the only way to get the integers, is if you start with the unknot. So here's an example to see how this works. It's another unknot. This time, if you look at that picture of K carefully, it might look at first like it's knotted, but after just a little inspection, you'll see that it's really just a pile of string that has not been tied. The overcrossings all cancel each other out. If you, in one way of looking at it, you could pull it straight in another. But let's find the fundamental group. This will give us another opportunity to see the steps that are required to find a presentation of the knot group. We get a generator for each of those arcs that I've labeled alpha 1, alpha 2, and alpha 3. The interesting one to look at carefully is alpha 2. It's the entire arc that looks like this picture on the side. It even crosses itself. So, and alpha 3 is a very short little arc. So that'll be important for the quiz. You'll have some similar pictures. All right, so pi 1 of R3 minus that knot has the 3 generators, and then there will be 3 relations because there are 3 crossings. So that first relation is where alpha 2 is the overcrossing, alpha 1 is the undercrossing on the at first, and after it goes underneath, it becomes alpha 2 again. In other words, this is the crossing at the top of the picture, the first relation. So we get x2, x1, x2 inverse equals x2. Then the next relation is at the bottom right of the picture. There we see x2 as the overcrossing, so it goes in first and last place with the inverse on the end. But the initial undercrossing portion is x2 again, and then as it passes under, it becomes x3 because it starts out as alpha 2 and comes out as alpha 3. Finally, the last crossing there, it's x2 again on top. So you have x2, x3 is the initial undercrossing portion, and then x1 is when it comes out the other side. All right, so this starts to simplify pretty quickly. You can take the first relation and just rewrite it by multiplying x2 inverse on both sides. Multiply first by x2 on the right. It looks like I did that first. So x2 times x1 equals x2 squared. In the second relation, looks like I just simplified x2 times x inverse is equal to the identity, so you get x2 equals x3. And in the third relation, looks like I multiplied by x2 on both sides to get x2 times x3 equals x1 times x2. And then x2 is equal to x3 means we don't need both of those. That's really just one generator. So I dropped x3 and just left it as x1 and x2. And then I replaced all the x3s in the list of relations with copies of x2. So now I have x2 times x1 equals x2 squared, and x2 squared equals x1 times x2. A little redundant there. Either one of those, as you see beneath simplifies to x1 equals x2. So sure enough, I only have one generator, x1, and no relations. And that's the integers. So the theorem is that this always happens. If and only if, in fact. If you start with the unknot, you get the integers. If you get the integers, then you must have had the unknot. So, a little note about that equivalence. This is not equivalence, which basically means that it's the same knot, just by pulling and stretching and moving the string around. The diagrams of the two knots are the same after applying the following three moves. Any number of these moves in any order. Basically, you can separate two overlapping strands, you can remove a loop, or you can pull one strand over top of the crossing of two other strands. So, first of all, there's a theorem that says that those three moves are enough to change any diagram of a knot into an equivalent knot. And then you can use those three diagrams to prove the big theorem there at the top, that the knot group detects the unknot. That it's equal to the integers if and only if the two knots are equivalent.